Hello, this is our second series of slides on nonlinearity where we did the Kahoot quizzes. So I'm going to go through this next section. This is, I think, the same data from the earlier one. Sorry. And so we can see here that we decided from our last why is this not working? Our last set of slides that we already determined that there was a nonlinearity in this data, because when you go from 5 to 10 milligrams for a dose, we would expect to go from 150 to 300, and we're going to 560. So there's a much larger increase in our area under the curve than we would have expected. And our area under the curve is equal to our bioavailable dose over clearance. So if our area under the curve is increasing more than we would expect, remember we expect this to be 300 and it's 560, then either there's been a nonlinear increase in bioavailability or a nonlinear decrease in clearance. So what are our choices here? Clearance must be decreasing with increasing dose. Yes, that is correct. Volume must be decreasing with increasing dose. Well, is volume a determinant of area under the curve here? No, so we don't even have to consider that possibility. How about clearance must be decreasing with increasing dose? No. This also is true. Sorry, I have the same answer twice, which is goofy. So this one is also true. Clearance must be decreasing with increasing dose. I probably meant to say increasing, but I didn't. So this is also true if you put this one. Volume must be decreasing, and volume isn't even a factor, so we don't even have to consider the direction. It's okay. Thanks. All right, so next slide. All right, this is the same data. Okay, so this one was given IV. I guess I even skipped that part, which is really bad. So bioavailability isn't an issue here, so it must be due to decrease in clearance. Now here, we have to consider bioavailability since it's being given PO, and this is that same data. So it could be due to an increase in bioavailability or decrease in clearance with increasing dose. So clearance is decreasing, yes, with increasing dose, and or bioavailability is increasing. Yes, this is correct, isn't it? This describes this perfectly. How about clearance is increasing? Well, if clearance is not increasing with increasing dose, it's decreasing, so we don't even have to read any further. Clearance is decreasing with increasing dose, and F is decreasing. No, F would have to increase, so that's not true, and we are not stumped. Okay, if clearance is decreasing with increasing dose or dose rate, what could explain that? So what causes a decrease in clearance with increasing dose rate? Well, clearance can be determined is determined by several different ways. If it's hepatic, it can either be due to blood flow or due to intrinsic clearance and binding. Blood flow will never have a concentration component to it, so that's certainly not going to be the explanation. But both intrinsic clearance, the enzyme activity, and binding could be nonlinear because they're both dependent upon Michaelis-Menten, right? So intrinsic clearance is dependent upon Vmax over Km plus concentration. So there is this concentration component, therefore it could be nonlinear. What's going to happen as we increase the dose or dose rate, as we put more drug into the system? What's going to happen to our intrinsic clearance? We're going to overwhelm those enzymes, and the intrinsic clearance is going to decrease, isn't it? So would that cause a decrease in clearance? Yes. So nonlinear intrinsic clearance is a possible answer, isn't it? How about binding? Is binding saturable? Absolutely. Is there a Michaelis-Menten component to binding? Absolutely. But what's going to happen to our fraction unbound as we add more and more drug? As we add more and more drug, there's going to be a greater and greater free fraction, isn't there? The free fraction unbound is going to increase. If our fraction unbound is increasing with increasing dose or dose rate, then our clearance is going to go up. So that does not explain this data, does it? So how about renal clearance? If we have renal clearance, we could have nonlinear filtration clearance, we could have nonlinear renal secretion, but we cannot have nonlinear reabsorption because there is no Michaelis-Menten component. There's nothing to saturate. But in this case, we know this answer is correct. So nonlinear Q is also not a possibility. It's a blood flow. It is not concentration dependent. It is not Michaelis-Menten. So the answer here is nonlinear clearance. If clearance is decreasing, I like to write right on. Let's see if I can do that though. If clearance is decreasing with increasing dose or dose rate, what explains this? If we know that the clearance is hepatic and it's a low E. Well, that's the same question as before, isn't it? If it's a low E drug, then clearance is dependent upon enzyme activity and binding. And we know that as we increase the dose, we're going to have a decrease in intrinsic clearance if it's nonlinear, but we'd have an increase in fraction unbound if this is the source of nonlinearity. So it can't be binding, it's got to be enzyme activity. So again, the answer is nonlinear intrinsic clearance. Whoa, what happened there? And just so, why is it not nonlinear binding? Because we're going to have a higher free fraction, which would result in an increase in clearance. And we want to know with decreasing clearance. So that's not an answer. Nonlinear Q is not saturable. Right? If clearance is decreasing, I like to write this down, or you can type it into your ExamSoft. With increasing dose or dose rate, what explains this if it's a high extraction drug? Well, if it's a high extraction drug, then clearance is approximated by Q, and so that can't explain it. It's not nonlinear binding because it does not determine Q. It is not nonlinear intrinsic clearance because that's not a determinant of clearance for a high extraction drug. It's not nonlinear Q because there is no such thing. So it's none of these, right? It's none of these. You can't saturate it. So you should not see nonlinear clearance in a high extraction drug. It's not possible. If nonlinear clearance due to saturable enzyme sites for a low E drug, what happens to the half-life? So if it's saturable enzymes, then what's happening? Then we have a decrease in intrinsic clearance as we increase the dose, right? Which results in a decrease in clearance for a low extraction drug. So what's going to happen to the half-life? Well, half-life is 0.693 volume over clearance. If we decrease the clearance, what's going to happen to the half-life? It's going to get longer. So it's not going to stay constant. It will increase with increasing dose rate. Absolutely. This is the answer, isn't it? It will decrease. Nope, it's going to increase. If nonlinear clearance due to saturable binding, okay, so this case, so what's going to happen with saturable binding? Well, it's going to increase the free fraction as you increase dose. Right? So what's going to happen to clearance? Clearance is intrinsic clearance times fraction unbound. So our clearance, if our fraction unbound is increasing, there's going to be more available to clear. So our clearance is going to increase. So what's going to happen to our half-life? 0.693 volume over clearance. As our clearance increases, what's going to happen to our half-life? It's going to decrease. So no, it is not going to stay constant. No, it is not going to increase. It's going to decrease. Oh wait, I am wrong here. Back up, because isn't binding a volume dependent upon volume? Remember, volume distribution is also a determinant of half-life. So what's going to happen to volume? If we saturate those binding sites, we're also going to have an increase in fraction unbound. So that increase in fraction unbound, let me erase this here for a minute. This increase in fraction unbound is going to increase the clearance, isn't it? It's also going to increase the volume to the same extent. So will there be a change in half-life? No change. Oh man, I almost missed that one, but no, I did it on purpose. So the clearance will be increasing, but so will volume to the same extent. So the half-life should not change. This is tricky, isn't it? This data shows a nonlinearity. Okay, let's look. 15 to 30. This is dose. This should be dose rate. First thing is a mistake here, isn't it? 15 to 30. So this should be going 2 to 4. And it's going to 7.6. So this is much more than what we would expect. So the dose rate, so we have a either a nonlinearity in bioavailability or clearance, don't we? So it shows a nonlinearity. Yes, it does. This is true. What could cause this if it was given IV and renally cleared? All right, so this is too high. Here we've got it correct. Oh no, this is still dose rate. So if it's given IV, we don't have to worry about bioavailability, do we? So it's really about dose rate over clearance. And it's cleared renally. Okay? And what's going on? We have a higher than expected CSS average, which means we have a decrease in our clearance as we increase our dose rate. All right, so where is their Michaelis-Menten? Let's see. Could it be, well, first of all, we have filtration, we have secretion, and we have reabsorption that occurs, right, in renal clearance. Filtration is a simple filter, and it's GFR, which is not saturable, right, times fraction unbound, which is. So if we saturate those binding sites, our fraction unbound is going to increase, which will increase GFR, which was filtration clearance. Is that what we're seeing here? No, we're seeing decrease. So it's not filtration clearance, is it? How about another choice? So it's not filtration clearance. How about secretion? Secretion is saturable, right? So if our secretion sites get overwhelmed, what's going to happen? Is more or less of the drug going to be moved into the tubule? Well, if those sites get overwhelmed, more of the drug is going to stay in the blood, right? Because it can't get a ride into the urine. Therefore, we're going to see a decrease in renal clearance due to a decrease in secretion clearance. That does explain it, doesn't it? So we know saturable renal secretion sites is a possibility. How about reabsorption? Is reabsorption Michaelis-Menten? Is there a saturable component? No. It's passive diffusion, so it is not saturable. So the answer here is saturable renal secretion sites. Zero order kinetics is also known as nonlinear dose dependent. Yes! That's important for you to understand. They're different nomenclatures. They have different nuances, but they're all one and the same. If a CSS average is increasing proportionately as the dose rate increases, this is an indication of nonlinearity. Increasing proportionally? No, that's expected, isn't it? CSS average will increase proportionally with dose rate as long as bioavailability and clearance are linear. So this is false, right? Because this is describing a linear situation. Which of the following are not saturable systems? Well, they have to have Michaelis-Menten. So is plasma protein binding Michaelis-Menten? Yes. Is renal tubular active secretion? Yes, saturable, because it's Michaelis-Menten. There's a fixed number of carrier sites to move. How about hepatic metabolism? Yes, a fixed number of enzymes. How about passive, the important word being passive here, passive reabsorption? That is not saturable, right? Because it's passive reabsorption. It's really about, well, a lot of things, but this is not saturable. There's no carrier system. So the answer here is, sorry, I circled, this is the actual answer, is renal tubule reabsorption. Which of the following could cause an increase in volume as dose rate increases? So volume is dependent upon the fraction unbound in plasma over fraction unbound in tissue. Both of these are saturable because they both have fixed numbers of binding sites. What happens if you overwhelm the binding sites? The fraction unbound in plasma will start to increase with increasing dose, and that certainly could cause it, right? If you saturate the tissue binding sites, it's going to increase and you're going to see a decrease in volume, so that's not it. So it's saturable plasma protein binding, not hepatic enzymes. Hepatic enzymes have nothing to do with volume. Neither does renal tubular active secretion. So that one's pretty easy. A decrease in the number of liver enzymes that clear a drug would cause a nonlinearity. Probably not. Intrinsic clearance, which is your hepatic enzyme activity, is Vmax over Km plus C. A decrease in Vmax is the capacity, the number of enzymes available. That will decrease intrinsic clearance, but it does not cause a nonlinearity. What does cause a nonlinearity is this relationship here. So this is false. Drug X's half-life increases as dose increases. So we're seeing increase in half-life. If it is Fe of 0 means it's hepatic, low E volume is clearance over fraction unbound in plasma. Remember what I forgot before, which is volume is also, I'm going to move this over here. Half-life is volume over clearance, which is intrinsic clearance times fraction unbound for a low E drug. So these two are going to fall out in importance, not because they're not important, but because they affect both volume and clearance to the same extent. So a drug's increase in half-life could either be due to a decrease in intrinsic clearance. This is going to decrease half-life, so it's got to be due to saturable enzymes, doesn't it? The answer here. Q is not saturable, so anytime you see saturable Q, you can cross that out right away because it isn't saturable. A saturable fraction unbound is going to affect both volume and clearance to the same extent, and so there will be no change in half-life. Drug A, again, is cleared by the liver, and a low E drug, which was given IV, so we don't have to worry about bioavailability. What would explain this? Okay, so we're going from 50 to 100, and this should go 1 to 2. So we have a decrease in the expected CSS average, don't we? So what would cause that? We don't have to worry about bioavailability. Dose rate we're controlling, so it's about clearance. Since this is a low E drug, if we saturate the enzymes, that's going to cause a decrease in intrinsic clearance, which would increase CSS average, so that's not it. But binding, we're going to see an increase in fraction unbound, which would decrease CSS average. So in this case, it's saturable fraction unbound. Remember, we can cross that out right away. Saturable intrinsic clearance would have caused this number to be larger than 2. And it's smaller than 2, so it's not saturable intrinsic clearance. When comparing these natural log concentrations versus time curves for Fg and Lm, it shows that Lm, which is the red one here, must have a much lower Km than Fg. Well, we can see this is linear and this guy's not linear. Patient Lm is not linear. So if we look at intrinsic clearance, if we know it, probably we need to know that it's cleared hepatically low extraction drug, but to skip those steps, remember it's all about this relationship, right? So if they're having the same concentrations, in order for, as long as this is true, then it's going to be linear. So this is patient Fg, this is the blue guy. Well, Km is staying much larger than concentration. So patient Lm must have a much lower Km, because this would no longer be true if the Km was small. Then that's our patient Lm. So this is true. All right, that's it. I hope that helps. All right, thanks.